In the previous lecture, we have been talking about the first moment of a plane area and its centroid. Continuing on that, in this lecture we define some more mathematical quantities and just work out some examples with them. The utility of defining such quantities would be clear later when you do rotational dynamics and so on, but in this lecture we are just going to restrict to their definition and working them out. The quantities I will be talking about would be 1, second moment of a plane area, two, transfer theorems. By transfer theorems, we mean how, if we know the second moment of a plane area in one particular set of axes, how do we transfer them to another set of axes. 3, we will be talking about relation between second moment and product of area. In particular, we will be focusing on how second moments and products of area, which we will define later in the lecture, change when we go from one set of axes to another set which are rotated with respect to the other. And then we will be talking about polar moment of an area. So, to begin with, let us define what is second moment and product of an area. And product. Suppose I am given an area, a plane area in xy plane like this. This is the x axis, this is the y axis. Then the second moment I x x about the y axis is defined as, I take a small area, let me make it in blue, delta A, multiply this by the perpendicular distance from the x axis square. So, I x x is defined as, take area delta A I multiply by its perpendicular distance from the x axis and add it up. This is the second moment of this area with respect to the x axis, and this obviously goes to the integration y square dA. Similarly, I y y, that is the second moment about the y axis, is defined as the distance of the area from the y axis is chosen, and then we write this as summation x I square delta A I, or in the limit of integration this becomes x square dA. These are just mathematical definitions, and then the product of this area is defined as integral x y dA, and I am going to call this x I x y equals this. So, we have defined the second moment of a plane area and product of a plane area. Let us now work out some examples of how to calculate these. As the first example, I take a square of side A and calculate for it the moment of inertia, moment of area about the x axis and about the y axis and its product of area. I x x is equal to, by definition, y square dA. To calculate dA, I choose a strip at height y, because for this entire strip the moment of the area is going to be the same. So, this becomes integral y square a dy, and y changes from minus a by 2 to a by 2, and therefore, I x x is going to be a times 1/3 y cubed minus a by 2 to a by 2, or this comes out to be a raised to 4 over 12. Similarly, to calculate I y y, this is the square. I choose a strip like this and calculate I y y as integral x square dA, which in this case would become integral, this is at distance x. So, integral x square a dx from minus a by 2 to a by 2, and this also in this case by symmetry would come out to be a raised to 4 over 12. Third, for the product of area, you see that I x y is equal to integral x y dA minus a by 2 to a by 2, and if I choose a small area dA here, this will be equal to integral minus a by 2 to a by 2 x dx integral minus a by 2 to a by 2 y dy, and by antisymmetry of the wave of the function x and y, this goes to 0. So, for a square of side A, I x x equals I y y equals a raised to 4 over 12, and I x y equals 0. As a second example, let me take a rectangle of length a and width b, placed symmetrically about the origin. So, this side is precisely a by 2, and so is this. It is not made to scale, but please understand this is a by 2 divided on both sides, and I want to calculate I x x. For that, again I choose a strip here of width dy, because for this entire strip y square is the same, and calculate integral y square a dy is that small area dA, and y changes from minus b by 2 to b by 2, and this comes out to be a over 3 y cubed minus b by 2 to b by 2, or a b cubed over 12. Similarly, when I calculate I y y, for that I choose a strip parallel to y axis and calculate integral x square dA, which now becomes x square b dx, x varying from minus a by 2 to a by 2, and this comes out to be a cubed b over 12. How about I x y? I x y again you will see by symmetry, because the area is equally distributed on the negative side and the positive side of the y and x axis, comes out to be 0. So, we have already also calculated the moment, second moment and product of area for a rectangle. As a third example, we will make it slightly more complicated, and I wish to calculate the second moment and product of area for an ellipse, a quarter of an ellipse here, with semi-major axis A and semi-minor axis B. The equation for the ellipse is x square over a square plus y square over b square is equal to 1. To calculate I x x, which is integral y square dA, I choose a strip parallel to the x axis of width dy and write this quantity as y square. The length of the strip, let us call it delta x dy. My job is to calculate delta x, and y varies from 0 to b. From the equation, x lower is 0, that is this point, and I also know from the equation of the ellipse that x is equal to a over b square root of b square minus y square. Therefore, I x x is going to be 0 to b a over b y square is square root of b square minus y square dy. This is what we got to integrate. To do this, we substitute y equals b sine of theta. By doing so, I get I x x, which is a over b integral y square is square root of b square minus y square dy 0 to b as a over b integral 0 to pi by 2 y square is b square sine square theta, b square minus y square root is going to be b cosine theta, and dy is again b cosine theta d theta, and this gives me, this b cancels and I get a b cubed integral sine square theta cosine square theta d theta 0 to pi by 2. This can be written as a b cubed divided by 4 0 to pi by 2 sine square 2 theta d theta, which is a b cubed over 4 integral 0 to pi by 2 1 minus cosine 2 theta over 2 d theta. Doing this integral, when we do cosine 2 theta integral, that gives me 0, and the first integral is going to give me pi by 4, and therefore, I get for this shape where this is a, this is b, I x x equals pi a b cubed over 16. Similarly, I can calculate I y y, which is integral x square dA, where now I am going to choose a strip parallel to the y axis. The integral is very similar to what we just now did, and this will come out to be pi a cubed b over 16. How about I x y? To calculate I x y, I have to calculate the integral x y dA, where dA I take to be a small area at point x and y. And this can therefore be written as x dx y dy. X varies from 0 to a, and for any given x, a given x here, y varies from 0 to a y upper, where y upper is given by the equation x square by a square plus y square over b square equals 1, and that gives for any given x that y is going to be b over a square root of a square minus x square. and therefore, I x y for this is going to be integral x dx 0 to a integral 0 to b over a is square root of a square minus x square y dy, which is nothing but 1 half 0 to a x dx b square over a square times a square minus x square. This is a standard integral. So, this gives me the answer a square b square divided by 8. Therefore, what we have determined is that for a quarter of an ellipse with semi-major axis A and semi-minor axis B, I x x is pi over 16 a b cubed, and I y y is pi over 16 a cubed b, and I x y is a square b square over 8. I will now leave it for you as an easy exercise to calculate I x x and I y y, that is the second moment of an area with respect to x and y axis for the entire ellipse, and also show that I x y for the entire ellipse is going to be 0 because of the symmetry between x and y axis. Using the second moment of area, we can also define something called the radii of gyration. By gyration, you can already see that these quantities are going to be useful when we describe rotation. The radius of gyration k x of an area A about the x axis is defined through the relationship a k x square equals I x x equals integral y square dA, and radius of gyration for about the y axis is defined as a k y square equals I y y equals integral x square dA. Thus, for example, when we look at a rectangle of length a and width b, we have already calculated that I x x is equal to a b cubed over 12, and therefore, k x square is going to be a b cubed over 12 a b, or equals b square over 12. Similarly, k y square is going to be a square over 12, and from these radii of gyration about the x axis and the y axis can be calculated. Having defined these quantities, the second moment of inertia and the product of inertia, we now describe a relationship between the second moment of an area about a set of axes passing through the centroid of the body and another set x y axis which are parallel to those passing through the centroid. Thus, suppose I have an area with the centroid with respect to a given set of axes x and y with origin at O, such that the coordinates of its centroid are x 0 and y 0. Let us choose another set of parallel axes x prime and y prime passing through the centroid. X prime is parallel to x and y prime is parallel to y, and we want to now show that I x x and I x prime are related by a very simple theorem, and so are the other moments. Thus, I x x is equal to y square dA. So, suppose I have a small area dA here, this is y, which is also equal to y is equal to y prime, where y prime is the y coordinate of the same area with respect to x prime and y prime axis, plus y 0 square dA, and this is equal to y prime square dA plus y 0 square dA plus 2 y 0 integral y prime dA. Notice that y prime square dA is the I x prime, that is the second moment of inertia about the x axis passing through the centroid, and y prime dA is nothing but area times the y coordinate of the centroid in the centroid frame. So, this is going to be 0. If I calculate the centroid with the origin at the centroid, the coordinates of the centroid are going to come to 0, and therefore, I see that I x x is equal to y prime square dA, that is I x prime plus y 0 square times the entire area. This way, if I know the second moment of inertia of a body about an axis passing through its centroid, I can easily calculate the second moment of inertia of the same body with respect to an axis which is parallel to the first axis, but displaced by amount y 0. In the same manner, we can now calculate I y y, which is equal to integral x square dA, which I can write as x prime plus x 0 square dA. Let me for convenience show in the picture again what we are talking about. This is the body, this is the centroid set of axes x prime y prime, this is x y o, this is x 0, this is y 0. So, if I choose an area here, this is x and this is x prime. So, x is x prime plus x naught. So, this can be written as equal to integral x prime square dA plus x 0 square integral dA plus 2 x 0 x prime dA. This again by the same logic as we applied earlier, that this is the x coordinate of the centroid in the coordinate system which has its origin at the centroid itself. So, this is 0. So, I get I y y is equal to I y prime plus x naught square a. So, it is as if the entire area is concentrated at the centroid plus whatever the moment, second moment of area is about the axis passing through the centroid. Next, let us calculate the product of area, again making these axes x prime y prime, x y o, and I take an area here. The product is I x y, which is equal to integral x y dA, and I substitute for x and y as x prime plus x 0, y prime plus y 0 dA, which comes out to be x prime y prime dA plus x 0 integral y prime dA plus y 0 integral x prime dA plus x 0 y 0 dA. Again by the arguments that we have used earlier, these two terms drop to 0, and therefore, I x y is equal to I x prime y prime plus x naught y naught times the whole area. So, what we have learnt is, if we know the second moment of inertia and the product of inertia about a set of axes passing through the centroid, I can calculate about any other set of axes which are parallel to those passing through the centroid. Let us summarize these. So, for an area whose second moment and product of area are known about the axis passing through the centroid, I have in general I x x equals I x prime plus y 0 square times the area, where y 0 is the coordinate of the centroid, y coordinate of the centroid, I y y is equal to I y prime plus x 0 square times the full area, and I x y equals I x prime y prime plus x 0 y 0 times the entire area. These are known as transfer theorems. Using these, I can transfer the moment of area or the product of area from one coordinate system to another. As an example of the application of the transfer theorem, let us take the case of an ellipse with its length being 2a and this being 2b, with its centroid at point x 0 y 0, and calculate its moment of area, second moment of area and product of area with respect to the x y axis shown here. So, by transfer theorems, I have I x x equals I x prime plus y naught square times the area of the ellipse. I y y similarly is I y prime plus x naught square times the area of the ellipse, and I x y is equal to I x prime y prime plus x 0 y 0 times the area of the ellipse, where I x prime is the second moment of area with respect to the x prime axis parallel to the x axis passing through the centroid. I y prime is the second moment of area with respect to the y prime axis parallel to the y axis and passing through the centroid. Previously, we have calculated I x x as pi over 16 times a b cubed for a quarter of an ellipse like this. So, for the full ellipse, and this I left as an exercise for you there, this is going to be 4 times as much. So, this is going to be pi over 16 a b cubed, which is pi over 4 a b cubed. Similarly, I y y prime for the ellipse is going to be 4 times pi over 16 a cubed b, which is pi over 4 a cubed b, and I x prime y prime is 0. Therefore, for this ellipse, we will have I x x as pi by 4 a b cubed, which is the second moment of area about the x prime axis passing through the centroid, plus y 0 square times pi a b, where pi a b is the area of the ellipse. I y y is going to be pi over 4 a cubed b plus x 0 square pi a b, and I x y is going to be 0, which is the I x prime y prime. By symmetry, it is 0 for axis passing through the centroid, plus x 0 y 0 pi a b. So, using transfer theorems, we could calculate the second moment of area and the product of area when it was given about the centroid. So far what we have considered in the transfer theorem is the product and second moment of area when the centroid is displaced with respect to the origin of a given system. Now, we want to look at another transformation where given an area and its second moment of inertia and product of inertia about a set of axes x y, we wish to calculate it about another set x prime y prime, which is rotated with respect to the first set by an angle theta. Let us see what happens in this case. So, if I were to calculate I x prime y x prime in the rotated set, this is going to be equal to integral y prime square dA. I y prime is going to be equal to x prime square dA, and I x prime y prime, and the second frame is going to be x prime y prime dA, where we choose a small area dA whose coordinates in the original system are x and y, and in the new system are x prime y prime. We can find out the relationship of I x x prime with those similar quantities in the unrotated frame by simple transformation laws of x and y coordinates. So, let us do that now. So, what we are given is an area and we wish to calculate its second moment of area and product of area with respect to a set of axes x prime y prime when they are given in x and y. We know from our previous lectures that x prime for a given point is equal to x cosine of theta plus y sine of theta. Similarly, y prime is equal to minus x sine of theta plus y cosine of theta. Using these, let us find what I x prime is. From the previous slide, we know this is equal to y prime square dA, where dA is a small area chosen. Y prime square is going to be equal to integral minus x sin theta plus y cosine of theta square dA, which I can write as x square dA integral sin square theta plus integral y square dA cosine square theta minus 2 x y dA sin theta cosine of theta. But x square dA is nothing but I x x, y square I y y, sorry, I y y, y square dA is nothing but I x x, and x y dA is nothing but I x y. Therefore, I can write this quantity as, let us go to the next page, I x prime as I y y sin square theta plus I x x cosine square theta minus I x y 2 sin theta cosine theta, which can be written as I y y divided by 2 1 minus cosine of 2 theta plus I x x divided by 2 1 plus cosine of 2 theta minus I x y sine of 2 theta, which is nothing but I x x plus I y y divided by 2 plus I x x minus I y y divided by 2 cosine of 2 theta minus I x y sine of 2 theta. Thus, if I know the second moment of area and product of area in one frame, I can calculate it in the rotated frame. Let us do the same exercise for I y y prime which is going to be equal to x prime square dA, but I know x prime is equal to x cosine theta plus y sine of theta, and therefore, I can write this as integral x square dA cosine square theta plus integral y square dA sine square theta plus 2 integral x y dA sine theta cosine of theta, which is, this is nothing but I y y, this is nothing but I x x, and this is nothing but I x y. So, this whole thing can be written as I y y over 2 1 plus cosine 2 theta plus I x x over 2 1 minus cosine 2 theta plus I x y sine of 2 theta, which is nothing but I x x plus I y y divided by 2 minus I x x minus I y y divided by 2 cosine 2 theta plus I x y sine of 2 theta. Last, we calculate I x prime y prime, which is nothing but x prime y prime dA, which is equal to integral x cosine theta plus y sine of theta times minus x sine theta plus y cosine theta dA, which comes out to be integral minus x square sine theta cosine theta plus x y cosine square theta minus x y sine square theta dA plus y square sine theta cosine theta dA. This is also dA. X square dA is nothing but minus I y y, this can be written as sine 2 theta divided by 2 plus y square dA is I x x sine 2 theta divided by 2, and x y dA is nothing but I x y cosine square theta minus sine square theta is cosine 2 theta. So, I x prime y prime is nothing but I x x minus I y y divided by 2 sine 2 theta plus I x y cosine of 2 theta. Let us summarize. What we are looking for is, if we know for a body the products and second moments of inertia in one particular frame, how about its values in the rotated frame? In the rotated frame, let me now write it in blue. I x prime is nothing but I x x plus I y y divided by 2 plus I x x minus I y y divided by 2 cosine 2 theta minus I x y sine of 2 theta. Similarly, I y prime is going to be I x x plus I y y divided by 2 minus I x x minus I y y divided by 2 cosine 2 theta plus I x y sine of 2 theta, and I x prime y prime is going to be equal to I x x minus I y y divided by 2 sine of 2 theta plus I x y cosine of 2 theta. What these transformation laws give me is, if I am given the second moment and product of area about a set of axes, I can calculate about any other set of axes which is rotated with respect to the first set of axes. Let me just illustrate this thing by a couple of examples which are very interesting. Suppose I take a circular area. For a circular area, no matter how I choose my rotated set of axes, let's take a third one like this, the circle always looks the same, and therefore, I x x and I y y should always come out to be the same, no matter what the cosine theta or sine theta is, and I x y should always come out to be 0. Let us see if that happens. So, I x x we saw already is I x prime is I x x plus I y y divided by 2 plus I x x minus I x y divided by 2 cosine of 2 theta minus I x y sine of 2 theta. Now, for a circular area, I x x is equal to I y y, and I x y is 0, and therefore, I x prime is going to be equal to I x x, and I y prime is also going to be equal to I x x equals I y y, and I x prime y prime which is equal to I x x minus I y y divided by 2 sine of 2 theta plus I x y cosine of 2 theta is also going to be 0. This is expected for a circle. What is very interesting, that the same thing comes out to be true for a square. Let us look at that case. So, if I take a square of side A, we have already calculated that I x x for such a square is a raised to 4 over 12, and so is I y y, where these are the x and y axes, and I x y is 0. The fact that I x x and I y y are equal and I x y are 0 makes these quantities the same, no matter which other frame you look at. So, let me write it in red, I x prime which is equal to I x x plus I y y divided by 2 plus I x x minus I y y divided by 2 cosine 2 theta plus I x y sine of 2 theta, this is not plus, this is minus, is going to be equal to I x x again. Similarly, I y prime is going to be equal to I y y, and I x prime y prime is equal to I x x minus I y y divided by 2 sine 2 theta plus I x y cosine 2 theta. This is always going to come out to be 0, no matter how much you rotate the axis by. So, for a square about any set of axes, I x prime is always equal to a raised to 4 divided by 12. I y prime is always equal to a raised to 4 divided by 12, and I x prime y prime is always 0. Having given these two examples, I use these transformations to define something called the principal set of axes. So, given an area, I look for those set of axes, let me call them x and y, so that I x y is 0, or rather give them a special name I x bar y bar, so that I x bar y bar is 0. How do we accomplish that? Since we already know that I x bar y bar is going to be equal to I x x minus I y y divided by 2 sine of 2 theta plus I x y cosine of 2 theta. This implies that if I choose rotate the new set of axes such that tangent 2 theta is equal to 2 I x y divided by I y y minus I x x, I will get new I x bar y bar is equal to 0. Such a set of axes where the product of area vanishes is known as the principal set of axes, and you can see from the construction that you can always find one set of axes, because tangent 2 theta is varies from minus infinity to plus infinity. You can always find a set of axes where the product of area would be 0. An interesting fact about the principal set of axes is that about the principal set of axes, the one product of area vanishes, and 2 the moment or the second moment of area is maximum about one axis, say the x axis, and minimum about the other one. If it is maximum about the x axis, the other one is going to be y axis. Let us see how does that come about. So, let us look at I x bar, which is I x x plus I y y divided by 2 plus I x x minus I y y divided by 2 cosine 2 theta minus I x y sine 2 theta, and ask for a new frame such that I x bar is a maximum. So, for that I got to do I x bar over d theta is equal to 0, and when I do that here, this implies that I x x minus I y y divided by 2 times minus 2 sine 2 theta minus 2 I x y cosine 2 theta is equal to 0, and that immediately gives me that tangent of 2 theta is equal to I x y times 2 divided by I y y minus I x x. So, when I accomplish by this rotation the fact that the product of area vanishes, at the same time it maximizes or minimizes the moment of area. This equation has two solutions. Suppose one of the solutions is theta equals alpha, and theta equals alpha plus pi by 2 is also a solution. So, by rotating it by angle alpha, I maximize or minimize the moment of inertia about that particular axis. You can show that about the axis at alpha plus pi by 2, it will be the other way. If it maximizes at alpha plus pi by 2, it will minimize, and vice versa. So, we found a set of axes principal such that not only the product of inertia vanishes, the second moment of not only the product of area vanishes, the second moment of area is also either maximum or minimum. If it is maximum about the x axis, about the other y axis, it becomes a minimum. If it is minimum about the x axis, it becomes maximum about the other axis, the y axis. Having made this point, let me now define something for you which is known as the polar moment of area. This is usually written as j, it is nothing but I x x plus I y y, and therefore, is equal to integral x square plus y square dA or r square dA. Given any area, r square for a small area chosen is independent of which set of axes we are talking about. So, this is independent of the set of axes chosen. And through this discussion, you also see that for a square, the any set of axes is the principal set of axes, because as we have seen earlier, the principal set of axes gives product of area 0 and second moment of area maximum or minimum. For a square, any set of axes gives you product of area 0. So, therefore, any set of axes chosen for a square or a circle is the principal axis. What we have covered in this lecture so far is the second moment and product of an area. A related quantity which we will talk about in later lectures when we discuss dynamics of rigid bodies would be the moment of inertia and product of inertia, and we will be using it then in describing the rotational motion of a rigid body.